All right, so again, recall that we had this. So that's a Cantor set, and what's true about Cantor set is X belongs to the Cantor set if and only if X can be written as 0.2a1, 2a2, etc. base 3. In other words, X can be written as a power series where n starts from 1 to infinity of 2a sub n divided by 3 to the power of n, where a sub n is 0 or 1. You remember why, right? 0 means you are to the left. If 2an were so either you are to the left, so that is 0, or you're to the right, which is 2. The middle thirds interval is represented by the 1. That's why this is a natural representation. And then this immediately shows that the set is uncountable. Clearly then, well, I should say maybe like this. So then we have Cantor function. Cantor function, we'll return to it still. And what is special about this function, it takes an element x, it looks at its tertiary expansion, and converts the expansion into a binary by deleting the 2's and changing the base to 2 to the power of n. Okay, and what we observed about this function, so first of all, that means that f is onto or surjective. So f is surjective, and the implication is that the cardinality of the Cantor set is bigger than or equal to the cardinality of the interval 0, 1, and that cardinality is equal to R, hence equality must hold. By the way, this cardinality can be represented as 2 to the power of aleph naught, because the cardinality of R, the cardinality of the continuum, is equivalent to the power set, the size of the power set of natural numbers. Okay? So I hope you remember all those things. So why am I saying that f onto the surjectivity implies that the Cantor set is having a bigger cardinality or equal to that of the real number line? Well, simply, how would I know that I hold at least as many fingers on my right hand as I do on my left? If there is a surjective map from right to left, that means there are at least as many fingers as on my left, correct? Because look at it, surjective, it means that I can take a subset and there will be a bijective map. You see what I do here? So this this set is strictly bigger because a surjective map exists, but no way I try can I produce an injective map. That's it. So far it's clear. Then other slightly more difficult property of the Cantor function. Maybe I'll show you how to do it. So the following: if x is less than or equal to y, where both x and y are elements of the Cantor set, f of x will be less than or equal to f of y. Maybe I'll just make strict inequality, otherwise it's not interesting, right? So if there is a strict inequality, so x is a point in the Cantor set strictly smaller than y, then f of x is less than or equal to f of y. This means f is increasing. So it's an increasing function, or maybe in calculus you call it non-decreasing, because it stays either at the same level or goes up. Equality holds if and only if x and y are the left and right endpoints of some deleted middle thirds interval. Interval. Okay, so in other words, what I'm claiming, what am I claiming? I'm saying that, for example, f of 1/3. Remember that 1/3 survives. 1/3 is the right endpoint of the left interval, and we delete the interval from 1/3 to 2/3. So the point that it's equal to will be f of 2/3. Agreed? So, I mean, maybe you don't agree with this statement, it's a little involved, but that's what it's claiming, you understand? So 1/3 and 2/3 are the left and right endpoint of the first middle thirds interval deleted. So the function will be equal. Also, you would find that the function f of 1/9 will equal to f of 2/9, and nothing else. Okay? So unless they are the endpoints, they are not equal. Let's actually maybe verify it for 1/9. So observe why this happens. So here is f of 1/9. I need to convert 1/9 into the Cantor representation. What is the Cantor representation? That would be f of 0.0 and then followed by 2's. Agreed? You agree? That's how I get to 1/9. I must go left and then again left, and thereafter I must go right. Can you see that? 1/9. So first I must be on the left interval from 0 to 1/3. Then I'm on the left interval from 0 to 1/9, and then I move right. So that's the representation of 1/9 without too much thinking. Now what does f do to it? F will simply write it as f of 0.01 hat. And I should emphasize that they are in different bases, right? So just like what's written over here, this is base 3. but this is base 2. Good? So what is this in base 2? Sorry, there should not be an f anymore. F did its job. So it's just 0.01 continued. So what is the number? This is 0.1, which is in base 2 equal to, what is 0.1 in base 2? And I thought you were following me. What is base 2? Could anybody tell me what is it that you do in base 2? How do you, so real numbers, it's just what you do is you measure by adding fractions, correct? So a real number is any measurement that can be carried with at most countably infinitely many additions of fractions. So to systematize, let's say base 10 system, how does it work? You measure how many integer units you have in a given length, and then if the integer is not quite enough, then what you do is you take that unity and you cut it into 10 parts, correct? So then you have plus either 1 over 10, or 2 over 10, or 3 over 10, all the way to 9 over 10, or 0 over 10, of course, right? So that's base 10. And then what do I do? If this is not enough, I just basically added the amount of 1/10 that I need to get to the supremum. And then what do I do? If it's still not enough, I add up a bunch of 100s. So I take 1/10 divided by 100, divided again by 10, and add the 10th of 10ths. And then 10ths of 10ths of 10ths. And I continue doing this until I reach the supremum. Remember, that's how the justification was produced. That's how you can express any number between 0 and 1. What you do is you see what's the biggest fraction in base P. Do you understand what I'm saying, guys? No. You see, I neglected you. I should have been, well, I should have been more strict. So, how do I know that any number between 0 and 1 is to be represented in base 2, for example? It's really easy to draw in base 2. So how would I represent, say this number over here? How would I write its decimal expansion for the number that I draw here? So that's my x. I want to prove that x has a base 2 expansion. So base 2 expansion, all that it means is that I'm going to write addition of fractions, all in powers of 1/2. Okay? So what I do is I take this number line, and what do I do with it if it's base 2?
1/2 plus.
Right, so I cut it, and I notice that this is this piece is length 1/2. So what I have is this x equal to 1/2 plus, okay, plus.
1/4.
And now you look at this thing. If I add another 1/2, that's too much. You see, I just add 1/2 to the point where I haven't moved across the x. Okay. So next, what do I do is the procedure I decided to do is to cut things in half. I could have decided to cut things in 10 or into 60. That's exactly the same idea, just harder to draw. Okay. So then I take this length, right? This 1/2, well, not quite good. I then take 1/2 of that. So I take 1/2 of that, and it's roughly somewhere over here. So it's 1/2 plus 1/2 squared. I moved one more. Okay. And then I'm not sure, right? What is this? If I cut this in half, it's too much, right? So what's the next number? The next is 0 divided by 2 cubed, and I continue doing it this way. So then, if I move by 1/2 cubed more, I move beyond the x. So I moved by 0 over half cubed, and then maybe I need to move by 1 over 2 to the 4. Etc. You see that this sum is growing. And in real numbers, what we did is we justified by the property that real numbers have supremum. Correct? Real numbers, they have a supremum. So this sum, because it's increasing and it cannot go beyond 1, the sum is bounded above, and therefore has a least upper bound. That's how simple it is. What do you do in why can every number be expressed in base 3? You do the same procedure, but you cut the line into 3 parts. And then you have possibility of adding 1/3, or 2/3, or 3/3, that's the full interval, okay? Or 0/3. I mean, you don't want to move by a whole 1/3, it's too much, okay? So that's how representation is in base 3 works. It works exactly the same in any other base. That's why it's clear every number between 0 and 1 can be expressed as an infinite sum of such fractions. Sometimes also as a finite sum of such fractions. Good? And then, what is this? 0.1 is what? Right, exactly. This is finally 1/2. So this number is 1/2. You see why? So this x, if I were to represent the x that is drawn over here, its representation is 0.110, etc. I don't know what's the etc. Understood? So f of 1/9 is 1/2. Let's calculate what is f of 2 nines. F of 2 nines. What is that? That's f of 0. Tell me what's 2 nines, please. 0 point what? What's the counter representation of 2 nines? To get to 2 nines, how much do I move? Do I move by a third? No, 1/3 is too much. So the first number here should be 0. And what's the next number? By the way, you know also that there is a possibility for office hours, right? You just never used it, right? So if you ever want to talk to me, I will come.
So 0.02
Yes.
is in base 3.
Is in base 3. So 0 and this is 2, right? Because what does it say? 2/9 is very nice. 2/9, in what form is it, right? 2/9 is the same as saying I move first by 0 1/3 and then by 2 3 squared. And then I can write the rest as 0.
No, I'm asking, we were up there 2 lines up, f of 1/9 is f of 0.02.
Right, I have to, for the function to work, I could have written the representation 0.01. But 0.01 is not the representation that is taken as input.
Way beyond what I'm asking you.
Okay.
I'm asking you, when you're converting, that 0.02 is in base 3.
That 0.02 is in base, by the way, this is 0.022222.
Yeah, but is 0.02, does that mean it's 2 divided by 9?
0.02 is 2 divided by 9, yes.
And that equals 1/9?
No.
It says f of 1/9.
No, look at it. There is. You see, so there you are right. I see what you're saying. There is an extra 0. Sorry about it. There is an extra 0 followed by 2's, right? First 0 is a third. I just miscounted the zeros. Then the next 0 is this, and then we have 2. Because you see what this is saying is, how do I know this is the representation without doing any thinking whatsoever? It's because I think where is 1/9, right? To get it by this motion of left and right, it means I first move left to the interval from 0 to a third, and then I need to move left again to the interval from 0 to 9, right? So that's first left, second left. 0 is left, remember? In the Cantor step. And then what do? To get to the 9th, I then continue moving right. So this is giving you direction. It's like saying, take 2 lefts and then continue taking right, and you will get to 1/9 by this sequence of nested sets. Thank you for noticing. Right. So that was an extra.
So 2/20. So that represents really like if it's just 0.002, that represents 2/27.
So let's see. So no, because the 2 continues. It's 2/27 plus 2 over 3 to the power 4, etc. So this is base, and I need to make sure that is it 1/2. So this is base Yes, and here I rolled it correctly. See, I eliminated one. So sorry, no. So this is base. So this is wrong, right? This is base 3. Base 3 now. It's base 3 now. And what should it equal to? It should equal, I messed up with one of the zeros, it should equal to the same thing but with one following. So it's 0.001 and the 1 continues forever. And that is in base 2. What is this number? This is the same as 0.01. 0.01, I just one zero is eliminated. Which is actually 1 divided by 4. You see that this is in base 2. This means I don't need 1/2. I take 1/2 squared. So it's 1/4. It converts base 3 to base 2.
Oh.
So this was base 3. It divides all the numbers. They are all either 0 or 2. It divides all of them by 2 and changes the base, saying it's written here, right? It switches the base to 2. So the digits that are part of the expansion are converted here.
So base 2, that's 1/16 at base 2, right?
So this thing, no, so be careful, right? So what is this? This 1 means it continues. It's 1, 1, 1, 1, 1. So what is this? This is 1 divided by 2 to the 3rd power plus 1 divided by 2 to the 4th power plus 1 divided by 2 to the 5th power forever. And that just happens to be the same as just moving a digit. Yes?
In that summation on the left, what does that n represent? Does that represent the base?
No, which summation? On which left?
So
You mean this part?
Yeah.
So look at this. This is just an infinite sum, a power series. Kind of like a geometric series. I didn't say. So this is a base 3 representation. You see, this is 3 to the power of 1, then 3 to the power of 2, then 3 to the power of 3, and this sum is infinite. And the numbers on the top are either 2 or 0. So an is either 0 or it's 1, therefore the number on the top is either 2 or 0. And what the Cantor function is doing, it converts the number into this form. Okay? So it's, again, as you see, you don't ask me, you don't come to office hours, don't email me. Do you understand what I'm teaching you? Do you watch the videos? No, you don't, most of you. Do you review this material? I don't know, I don't see this. So, what is this going to do? You see that 2/9 I can write this way. What's going to happen to this number? So 0.02 followed by zeros becomes what? 0.01. Everything is divided by zeros. And now this guy is in base 2, which is therefore 1/4. You see that? So what I just showed you is that f of 2/9 is equal to f of 1/9. And then hopefully you will follow the argument when I explain why f of x is less than f of y and equal only in the case where they are left and right endpoints. For that you have to understand this expansion. We talked about it at the beginning of the semester. We did this division to represent, you remember we calculated whether 1/5 is a member of the Cantor set. Remember we found the expansion in base 3, so this thing you have to be very comfortable with. So, okay. So let's try to see this general statement. So again, let's try to see why inequality holds. And help me, please. So why is this true? Let's see. So we have x is an element of the Cantor set. So x is equal to 0. It has this representation in base 2, right? In base 3, I'm sorry. 2a1, 2a2, somewhere 2an, etc. Right? So each an is 0 or 1. Okay? Now, if y is bigger than this x, if y is bigger than this x, what would you find? What would you find true about y? What's the expansion on y? So let's say that some of the coefficients are the same, so they agree to the first n coefficients. Agree? Y might have an expansion that's different on the very first coefficient, correct? Or it might be different on the second coefficient, or it might be different on the nth coefficient. So let's say that they agree on the nth coefficient. Okay? So in other words, the expansion of y is all the same. So they agree up to the nth coefficient. Right? But they're different. They're supposed to be different. So now tell me, please. Now there is a disagreement on this coefficient. There is a disagreement on this coefficient. Okay, now it's vital. I need your help. Okay, they disagree on this coefficient. Think about it very carefully. This is the first time the y and x are different. Y is bigger than x. What must be the coefficient here, and what must be the coefficient here?
0 and 0.
Are you sure that's the only way? Right? Because maybe this has a smaller coefficient than this guy, but it makes up for it with coefficients that follow. You understand what I'm asking, right? So how can you be sure that this has to be 2? You agree, right? This has to be 2, you think, right? And this has to be 0. They are all elements of the Cantor set. That's the first disagreement. So I'm claiming this is 2 and this is 0. How do I know that?
It can't be bigger or equal using the decimal expansion, because then it would have to be a 1 afterwards.
Right. So you see, I'm going to wave my hands, and I hope you follow me. Please try to follow me. Okay. So suppose that it's the other way around. Suppose this is 0, they're different, right? So suppose this is 0 and that's 1, okay? So how small can y be? If this is a 0, all the other, y is bigger. So if this is 0, let's say y tries to make up for the 0. It's supposed to be bigger than x, okay? So what it's going to do, it's going to try to make up for the zeros. And what is it going to do? So if this is 0, then all the others, it's going to make 2. To try to somehow gain. Let's say that's the best it can do, right? It tries to be as big as possible. So if this is 0 and all the others are 2, the most all the infinite 2's can do is change the 0. You can delete all the many 2's and change them to a 1. Do you understand that?
But then it's not.
Right? No, 0 to the 2, that's fine. It could change to a 1. But then what follows x? This is already 2. And whatever follows x, it could be that the x is trying to make itself as small as possible, and therefore everything following x are zeros. But even so, this is a 2 and this is a 1, but followed by zeros. Do you follow my argument? I don't want to write it too much, but you understand, right? That this has to be, if y is bigger than x, this has to be 2. There's no other way around it. So this is 2, and this is a 0. And I don't know what follows. Agreed? But if y is to be bigger, this has to be a 2 and this is a 0. Because if that's the first place where they're different, if you reverse 2 and 0, you see that y is smaller, no matter what you do. Okay? So that's what happens. And now let's try to understand what's going to happen to the function. So let's see if I take f of x. What do I get? I get 0.1 A1, A2, blah, 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 all the way to A sub n, followed by zeros, and followed by a bunch of an plus 2, etc. Agreed? And on the other hand, if I expand y, what do I get? I get that, I'll write the expansions number lower. Maybe I'll put in the lines in between. So what is f of y? F of y is very similar. It's 0.a1, a2, an, and then this 2 becomes I apply the Cantor function. So this is in base, this was base 3. This was base 3, but this is base 2. Look at what the function is doing. It converts bases. Right? It divides the numerator by 2, which it can always do because either the numerator is 0 or it's 2. And it changes the base to 2 to the n. So what is f of y? So this would be a sub n, followed by, what's here? 1. Followed by, I don't know the next might be different. So followed by bn plus 1, etc. Agreed? So afterwards, I don't know what happens. I just compare those two strings until the point where they differ first, and that was in the n plus 1th place. This should be n plus 2. So they agree all the way to the nth place. The first disagreement in the n plus 1th place, and afterwards I don't know. So this is just some other number. I'm not sure what it is. Okay. Now I want to compare those two numbers. So this guy, it's going to be less than or equal if I do what? So this f of x is less than or equal if I take a1, a2, an, and this again, the next one is 0, and then I want to make this as big as I possibly can. So the others, all the other strings are 1. You agree? Maybe they are not. I don't know anything about x. They might not be. But I make the number definitely not smaller by just replacing all the others by 1. I'm just trying to make it as big as possible, right? On the other hand, so what is this? So this is then simply 0.a1, a2, all the way to an, and then followed by just 1, and then followed by a bunch of zeros. Right? You see, I can remove the 0 and I can make it a 1. Okay? And on the other hand, I can try to make f of y. Then look at it. It's going to be smallest if I replace all the bn plus 2. If I replace them by 0. Agreed? So if I replace all those by 0, now I can put inequality. Look at it. This number here is slightly bigger possibly than this number, right? So I can put one more inequality sign. And we have this statement. Okay? So you see what I just did. F of x, blah, 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 less than or equal to f of y. So I already showed the function is increasing. Now, how could all those things be equalities? How could this be not an inequality, but an equality? It means that this thing is equal to this thing, which means that all the a sub n plus 2's are 1, right? And all the bn plus 2's are 0,
Which is the right one.
right? Which is the right and left point. You see that? So because what happens when I multiply those digits by 2? Look at it. So what were the original ones? The original ones was would be basically equality. If you just look at this inequality, it's equality precisely when this is 0 and when this 0 can be converted to a 1, which is exactly what happens when you move to the 1. Basically an element of the Cantor set that terminates in 1. It means it's about to be on the left edge, right? So if it terminates in 1 followed by zeros and it's an element of the Cantor set, it's the left endpoint because it wants to get to the middle thirds interval. And this, when it terminates in a 2 followed by zeros, that's the right endpoint. Do you see that? Yes?
You changed it to base 2 so it would be easier to work with.
All of this is, again, when I change it, this should be obvious. I don't need to repeat that it's base 2 because that's what the function is doing. This is base 2.
No, I know, but you changed it to base 2 from base 3 to make it easier.
No, to make what easier. So why you consider this function? That's a whole other story, right? So maybe one reason we consider this function is to show yet another way that the size of the Cantor set is, the cardinality is as big as that of real numbers. Okay. Another thing to think about it. Do you understand what the Cantor set looks like? Is the Cantor set closed or not closed? First question. Is the Cantor set a closed set? Remind me, please.
Well, is the complement an open set?
Let's now. I'm going to erase this part and let me just give you a few questions right? Just see where we stand. How many of you, by the way, will be taking second semester analysis? Could you raise your hand if you will? Good. So I'm not worried. I suppose. I suppose whatever job I did doesn't matter.
Trust me, you haven't met the other math professors.
No, I mean,
Then I'm
so
sorry.
I don't know. I met enough.
Yeah, that's how I feel.
I suppose. I mean, to myself, I sound understandable. Maybe not to you anymore, but to myself, I understand what I'm saying most of the time. So questions. Let's ask a few questions. Sorry? Oh, please. Questions about Cantor set. So question 1 is the Cantor set closed? Let's see if we can answer this. Is the Cantor set closed? Now, do you remember how it's constructed, right? You begin by taking, here, I can illustrate it this way, right? So here is my unity. This is, I suppose, left. This is the right interval, right? So what do? I remove the closed 1/3, right? So here is what I have now remaining: the right red and the left black. So when I carried out my first removal, is the set open, closed, neither? What survives is this segment and this segment. Is what surviving? What is surviving? Is it a closed set?
It's closed.
It is closed, correct? Because you can see that the complements are just open intervals. Now imagine that I do the same thing. So now this is like my unity, and I cut away the open middle thirds from each of them. What survives? Is it closed or not?
Of course.
And if I continue this process on and on and on, will the process keep giving me closed sets?
Well, not necessarily, because the union of closed sets isn't always
But
closed.
are we taking a union? Right? Yes, the union of closed sets is not necessarily closed, but is it a union that we're taking? Think about it, right? So what's the picture?
No, we're taking the interjection.
So here
Intersection.
is, let's say, this is I0. Start at 0, doesn't really matter. I7. You can start the intersection from any level, because you see what is the intersection going to do? It's going to do the same thing as if you go down the ladder, go all the way down to the counter. Do you agree? And now what is this? So this is intersection of what types of set? Of closed sets, and therefore the Cantor set is closed. Remember, right? If you do unions, you might mess up. Of course, here it's not so difficult. So that's one question. Good, it's closed. Thank goodness we figured that out. So question 2, let's recall. Very simple question: is this countable? We already answered this many times, and the answer will be.
Well, you said it has the same cardinality as the real numbers.
Well, that's what I said, but why? Why did I say this? Maybe I was not in a good mood.
It's uncountable.
Why?
Because they get so small that they start to include irrational numbers.
Yes, please.
But you said you could like map every like element of the Cantor set to an element of the P natural power set of natural numbers.
Yes. And now, how do I do this? I can designate the address of each point that survives this process as
Left.
let's say 0 to mean left, and well, maybe even let's not even use. So let's just say left. So this is then moving left again. So this means actually moving 2 lefts. Right, this is 1 left, this is 2 lefts. On the other hand, what is this? This means move left and move right. So first you moved left and then you moved right. Right, so this interval means you moved twice to the right. Whereas here you first move to the right and then you move to the left. So you see that, so what do you see? So the points of the Cantor set are those that survive the middle thirds deletion. So they have to survive it all the way down. And notice, to survive the first level, you must have an address of left or right. Surviving the second level, you must have 2 letters of address, left, right. Right? It's made out of all possible 2 letters. That's to survive to the, there should be 2 here, right? To survive to the second level. To survive to the third level, you see each of those intervals is again split into 2. So you now have to represent that by 3 letters. So we saw that basically that the Cantor set, the size of the Cantor set is the same as the size of infinite sequences of left and right. And that's uncountable. Because remember, that corresponds to the attendance roster of a class that has natural number many students. Because left is like saying absent, 0, let's say, again, by association, and right will be to say present. So that cardinality is easily seen to be infinite from that. And why do we know that the sequence of an infinite sequence does represent a point in the Cantor set? Now remember, we are in R. And in R we have this nested set theorem. Remember that theorem approved. The nested set theorem tells us what? Tells us that if I go, let's say, if I go through those addresses, they correspond to a particular nested sequence of intervals. And such intersection of a nested sequence of closed bounded intervals must contain points at the end of it. The intersection is never empty. But furthermore, if the intervals shrink to 0, the intersection can only contain 1 point. We argued that, correct? So for example, the sequence left throughout, left, represents what number of the Cantor set? 0. On the other hand, if I go left and then follow all the way to the right, so first left and then right, that represents what number? 1/3. right? So you see any sequence that you will take, sometimes it was not going to be comfortable. I will not know a good name for it, but we have that the set of the size of the Cantor set is the size of infinite sequences of left and right. They are in one-to-one correspondence, and that size is 2 to the power of Aleph. No.
Does it satisfy Archimedean property?
What does? What do you mean? Archimedean property is when you select a real number, where you select two real numbers, right? Here is a real number and here is a positive one. And you take this positive number and you begin multiplying it by an integer until it's bigger. So the Archimedean property tells you something very simple. Take let's say a number like 1 billion, and take a tiny number like, I don't know, 1 divided by 100 million, right? Eventually, if you multiply that small number by some large integer, it's going to be bigger than the million. So that's what the Archimedean property is doing for all real numbers. What it says is something rather intuitive. It tells you, take any positive real number. If you multiply it by a large enough integer, it's going to be bigger than any other test positive number. It's going to be immediately bigger than the negative, but it's going to be bigger than any positive number that you set against it. And that's where it's Archimedean. It's like you have this lever. You get more strength, you leverage by multiplying by the integer n. Okay, so in here we just talk about intersections. All right, so the set is infinite. Let's see what else we know about. Question 3. Now a slightly harder question. Is it perfect? Is it perfect? Do you remember what perfect sets are? Would anybody remind me, please? What is a perfect set? What must be true about it? Right, don't look into notes. I mean, it's easy to remember this. What's perfect? What's perfect is when you're not like I feel right now. Not like what I'm feeling now.
Isolated?
Exactly. Nobody is supposed to be lonely, and I feel extremely lonely in this class, right? So a perfect set is what? Is one where any member of this club, there is a club, and in this club every member is never isolated. Every member is a limit point of other members of this club. And this club is exclusive in essence that nobody that's part of this club is ever surrounded by such points. It's never a limit point of them, right? Or the set is empty. The club is empty, that can be perfect, okay? So the Cantor set, is it perfect? Well, one thing, it has to be an exclusive club. Is it exclusive? Yes, it's closed. Exclusiveness means closed. Remember, that means that any point that is not part of the Cantor set is not a limit point of that set. Because closed sets eat the limit points. They make them part. So the Cantor set is closed, therefore it's exclusive club. Is it perfect? Think about it carefully. So all that remains is that no member of the Cantor set is truly isolated.
But if we look at I1, for example,
Right.
that's definitely not, well, is it perfect? You can't, left and right aren't together.
But they don't have to be. Not every point has to be next to every other point. That would be impossible, right? All that matters is that no member of the set is ever alone. That if you draw even a tiny circle around any member of the club, there are other points from that club next to it. So clearly right is not next to the left. They are parted. But other points, perhaps?
It's never going to converge to one. It's always
What is it? What's not converging to one?
Like it's never going to converge to one certain point.
What is it?
The Cantor set, like.
Well, Cantor set is just a collection of points. When you say convergence, you talk about a sequence. What sequence is not going to converge more? So, any ideas?
It's not perfect because it's like discrete points.
Are they discrete truly?
No.
Yeah.
If they are, then you are right, but is it going to be truly discrete? So you're seeing deletions of those intervals, and you see that those islands, they get separated from other islands. The intervals are far away from other intervals, perhaps. But look at it. At each stage, is this a perfect set? I1, is it a perfect set? Yes, because look at it. So any member of the left group has friends on the left, and any member on the right interval has friends on the right. Right? So I0 is perfect, I1 is perfect, I2. Yes, right? They just clustered into their cliques. Right? So there is this left-left group, there is the left-right group, but there are still, nobody there is alone. And on the next step, it's going to be the same. Is it always going to be the same if you continue down the line?
Yeah, because it's going to be a union of those perfect sets.
Not a union, again. How is it a union? We remove parts,
What I'm
right?
saying is
So
those
we
little
take a bunch of
elements.
them, boom, we cut the crowd out. So they leave, they take the taxi, they go home.
In IN, when you get to infinity, I infinity, there's still small little perfect islands, and you take the union.
Are there? Each interval that survives is getting to 0. There is no room. So, do you see this? What I'm going to claim is that every point in the Cantor set is a limit point of its endpoints, of the right, left. So every point x, which is a Cantor set point, is a limit point of the endpoints. Okay? So I'm going to try by pointing my finger to illustrate what I mean. So do you agree that when I do the deletion, the endpoints of the interval are going to survive? So this point will remain in the Cantor set because it's never going to be deleted, because only the middle third is removed. And so is this point, and so is that point, right? So let's look at a particular point that survives, right? So if the point is neither left or right, when it survives, it's always surrounded by two friends, at least two friends. There may be a bunch leave, but in the interval when it survives, there is always two friends that are left friend and right friend. So a point that is not an endpoint is always a limit point of left and right. Not of the same, look at it. So first, the point had this left and this right friend. Next, let's say if the point is ending up in here, it has the old left friend, but already a new right friend. And let's say if the point was to survive and it stayed in this interval, then the left friend changed. So if I jump through the sequence, I will have a different pair of left and right friends. But they are clearly limit points. Do you see that? Because clearly, no matter how when you think, you have a small and smaller interval. Remember how you decide if something is a limit point. You take this x, you draw a circle around this x, and if in that circle there are other members of the club, then the point is never lonely. No matter if it's true, no matter how small is the circle. So if I take a tiny circle around this x, eventually the interval is going to be so small. This interval is going to be so small that it's entirely will be inside of the circle. Do you see that? So I take a circle. The circle has radius maybe 1/1,000,000. I don't know. Very small circle around that x. Now if I take 3 to the million, that's going to be so much smaller. You don't need to go that high at all. But 1/3 to the million, it's going to be really, really tiny, tiny interval. And it's clearly going to be inside of that circle. You follow? So the intervals, they vanish in size, they become small. So small that eventually the interval containing x will be contained entirely in a circle that you drew around that x. So you always see that every x that is not a left or right point is a limit point of both left and right. Agreed? So all those points are not lonely. On the other hand, if a point is a right point, if a point is a right point of some interval, it will always have left friends. It survives on the left, so it will always have friends on the left. That different friends. So the friends are replaced, different friends on the left. And if the point is a left-hand point, it has friends from the right. So regardless, I hope I explained to you that every point that belongs to the delta is a limit point of the endpoints of the intervals. So it is perfect. Yes, delta is perfect. So now question 4. Can you tell me something about the interior? So if I take the interior of the Cantor set, what is that equal to? The interior, do you remember what interior is? So which points have a whole full neighborhood around them? In this case, it's a one-dimensional neighborhood, so that would be an interval around them. Yes?
I want to say it's empty.
You want to say it's empty. All right. Anybody wants to say something different?
I'm thinking of that example where we have that isolated point, where we have an interval and an isolated point. The interior includes only that interval and not that isolated point.
So you're absolutely right. And let's try to see why it must be empty. Okay? So suppose x is sitting on so suppose that 1x has an interval. Right? Now, if it's to survive all the many deletions, you agree that this interval eventually is smaller than 1/3 to the power of n for some n. You agree? So if interior is not empty, that means that some open interval, no matter how tiny, somewhere survives through the deletion. So for example, in here, the size of the open interval that survives at 0 deletion is at most 1, radius 1. Right? Here, if I take an interval in I1, the biggest interval I can possibly produce that is open will be of radius, it would be of diameter 1/3. It will be of diameter 1/3, radius 1/3 over 2 or 0.6, right? So the biggest interval here has diameter 1. The biggest interval that I can find anywhere in here has diameter at most 1/3. In the next stage, the diameter is at most 1/9, and etc. Do you see? So could an interval survive? Because if the interval is so tiny, eventually it's still too big to because at some level set the biggest intervals you can have diameter no more than 1/3 to the n, and 1/3 to the n can be made smaller than the diameter that you picked. Do you follow me? You see, I'm just holding the interval with my fingers. Do you understand the argument? So the answer is that the interior is empty. The interior is empty set. It has no interior. In other words, it's a very bad it's a very bad herd arrangement, right? The Cantor sets are very vulnerable from being attacked by creatures that are not part of the club, right? It's not a very secure club. Understood? So if the interior is empty, what can you say about whether the set is dense, nowhere dense, etc.? So question number 5. Is Cantor set dense, not dense, lower dense, so in fact I ask you 3 questions. Is the Cantor set dense? Is it dense? Do you remember what dense means? So, for example, I mean, like, this is not quite, it's not static, but let's say if you go to China, right? The set of Chinese people in China, it's a dense set, right? Why? Because every person in China is either Chinese or one next to him is Chinese. So that's what dense means. It means that this set, if it were to be dense, elements from that set are arbitrarily near any member that's not in the set. We do know, because it's perfect, we know that every point of the Cantor set, it has members of the Cantor set arbitrarily near it. Right? So no point of the Cantor set is isolated. But is it dense? The answer is, how do we know it's not so basically we do this. When you take density, we see if we were to feed all the limit points, will it convert the entire real number line into basically, so you just do this. So you take the closure of the Cantor set, and the closure of the Cantor set is what?
Is the interval inside.
What's the closure of the Cantor
0 to 1,
set?
excuse me.
Sorry?
0 to 1.
No. What's closure? Now we forgot about closure.
It's the empty set.
No, closure.
Closure closes it. It's everything.
The Cantor set is closed. What's the closure? Closure is what you do. You take the set and you feed its limit points. You understand? So basically, if you take a set, if it's not already closed, what do? You feed the limit points. The official definition is what? It's that it's the smallest closed set that is properly, or not described, but that it's the smallest closed set that contains, in this case, the Cantor set. That would be the closure. But it's already closed. Therefore, it doesn't need to eat any more limit points. So what do you get when you take a closure? What do you get? The same thing. And that's not equal to R. So, not dense. So it means not dense. Okay, is it nowhere dense? Remember, those two things are not the same, right? To be dense means that I can, when I try to create neighborhood, when I try to convert limit points into members of the club, I will create, in this case, the entire real number line. That's what dense means. Nowhere dense means something much weaker. So, is delta nowhere dense? Class finishes at what? At 6:50, correct? Okay.
Dense on its endpoints?
Huh?
Dense on its endpoints?
What is, so when I say something is nowhere dense, remember that the language again might be slightly confusing, but I tried already to give you a good analogy of that. Think of let's say Brighton, and if you look into Brighton, you might ask yourself, is the set of Russians in New York a nowhere dense set? And the answer would be
Yes.
no.
Oh, that's right. 'Cause there's-
Well, remember what is nowhere dense? Nowhere dense means that they are not about to take over any neighborhood. But on Brighton, no, that's clearly not the case, right? So what is a nowhere dense set? So if you take Germans in New York, there is no neighborhood that is almost entirely populated by Germans, right? So what do you do when you ask nowhere dense? You don't look at the global space. You just look into a neighborhood of the space. Okay? Look somewhere in the space. So for example, with Russians, look at Brighton Beach. At Brighton Beach, everybody is either Russian or standing right next to one. Yes? So therefore, if you feed the limit points, the interior will not be empty, right? They're almost about to take over the neighborhood. But Germans, for example, in New York, you don't find a neighborhood that is big enough to take a neighborhood. So what does it mean in mathematics? What you do is you take delta, and then what do? You take the closure, and then once you take the closure, can you take the infinity, right? So closure means this. It's like in Brighton, if every Russian, since he's next to, basically either in Brighton, everybody is either Russian or right next to one. So if the guy next to him will to touch him and make him into a Russian, the full neighborhood will be only Russian. Okay? But with the Cantor set, if I take the closure, what do I get? You already answered this, right? If I take the closure, I just don't do anything because it's already a closed set. And if I take the interior, it is empty. And that means that the Cantor set is very sparse. You see, it doesn't have enough limit points to create itself a neighborhood, to create itself an open set. So delta is nowhere dense. Agreed? Yep.
What's the opposite of nowhere dense?
Not nowhere dense. Not nowhere dense. What is not nowhere dense? Again, don't forget about the language. Very simply, not nowhere dense means like the Russians in New York, right? You have neighborhood in Manhattan that it's not really crowded by Russians, so it's not about to be taken over by them. So that's not a good neighborhood, but we find somewhere in New York, we find a neighborhood that is almost Russian. And that means that it's not nowhere dense. You understand? That's how simple it is. Dense means you have so many that they're about to take over the entire neighborhood. Not just neighborhood, all the neighborhoods. The entire, if New York is what you call a neighborhood, they're about to take it over. Okay?
It's just the terminology.
Yeah, it's nothing else. It's so simple, right? What is there to think about? Terminology. Open sets, do you remember what open sets are? Right? Goodbye.